Hello, welcome to our second kind of lesson on hypothesis testing. Earlier, we spent a lot of time on writing hypothesis statements, like the null hypothesis and the alternative hypothesis, and we kind of set a lot of this up in class. But as we have a few people absent, I wanted to make a video on kind of the examples where we actually get to do our hypothesis testing. So kind of to recap a few things or kind of lay out some steps of how we're going to do this. We're going to start with just writing our hypotheses, our null and our alternative. And the other place we're going to go is we'd like to, in the same step, I want you to kind of, not required, but I would like you to write what type of test, because that can kind of help us set up the hypothesis, whether it's left-tailed, right-tailed, or two-tailed. Okay, a lot of people forget to pay attention to this detail, and it kind of leads them astray as they're doing their analysis. So first, just write our statements. Second step is we're going to collect evidence. If we were real statisticians doing real stats, we would have these statements and then we'd go out and set up an experiment where we have to collect data, do surveys, or go monitor something or go measure something. This is going to mostly be done for us in our examples. We're going to pretend like we did the collecting of data. And then the most important step is the analyzing of the data, which actually isn't that hard. All we're going to do is end up putting things on a number line or on a distribution, and that'll make the decisions for us. Okay, and that's kind of what I have written here is um, we'll do this just by drawing the distribution of the null hypothesis. It's very important to remember a few details here. One is that we assume the null hypothesis is true. We discussed this in class last time where it's kind of like we have even more potency to our argument if we say, okay, assume you're true. Let's try to prove you're not true, even using your own assumptions, using the null hypothesis. This is assumptions. Okay, so we're going to assume this is true and try to prove it false or try to reject it. And we're gonna draw the distribution and we'll label a few things. We're gonna label where the rejection region is and put our own data on there to see where we fall, and that makes the decision for us. Okay. So a few other things we may need for this, some formulas, of course, just to get z-scores, and I'll talk to you about why we care for having the z-score formula um, whenever we hit an example. Other ones we may need are kind of going backwards from z-scores. So if we know what the population average is, that would notice I have the little subscript of the 0 there because this is what the null hypothesis is assuming. We're going to have our critical value, or our z-score, and our standard deviation divided by the square root of the sample size. Because I don't truly know the population standard deviation, I'm going to estimate it with a sample standard deviation. So maybe I should have used a lowercase s there, but I think that's what the textbook uses, is a sigma. Same thing for two-tailed, same formula, but notice instead of an alpha, it's alpha divided by 2. That should make sense when we look at the drawing. We've discussed that in class. So let's jump into an example. Okay, so it says economic times are getting difficult with inflation hitting everyone hard, and it feels like inflation's starting to hit the companies too. Your favorite cereal brand, you think they're putting less marshmallows in each box. Oh no. The company claims that each box of cereal contains 16 ounces of marshmallows, as it always has, but you swear that it's less than 16 ounces. So you and your friends take action. It's time to begin something, so we start to measure the amount of marshmallows in all of our boxes. So we go get all that we can, and we end up with a sample of 9 boxes. So we go ahead and do some statistics, and we sample or take the average of our sample. It's 15.3 ounces and found a standard deviation of 1.2 ounces. So we're going to do a statistical test. We're going to set our alpha, or our level of significance, or significance level, at 5%. Okay, and that's important because that determines where our rejection region is. So question, are they putting less marshmallows in the box, and what can we conclude? So the first thing we need to do is make our statements. And let's see, so to make our statements, remember when we do this, we want to have the null hypothesis, and that's the statement of like no change, nothing, null. Like what are they claiming? That's the original claim, and they're claiming that the average amount, we'll write it as a population average, the average amount of marshmallows in there is 16 ounces. That's the claim. There's 16 ounces in the box versus, now We think what we're hoping to show, we believe our alternative, that it is less than. So we believe the population average is less than 16. Okay? Now, from here, this is the part I was talking about. I would like for you to be able to label what type of test you have. If you look at your alternative, it's a less than one, which means I have a left-tailed test. Why is that important? Well, it kind of lays out how we wish to draw our distribution. So if I'm going to draw this distribution, we're going to kind of assume it's a normal curve for now. We'll talk about that later. Maybe a bad assumption. We will work out those details. This is our introduction to hypothesis testing. So if you're watching this and you're not in my class, just hoping to get some help, there may be other areas we need to kind of take this. But on the surface, we're just going to start by assuming it's normally distributed and working with that. Okay. Now, this is going to be the distribution of this null hypothesis. So I know a few things on there. If it's normally distributed and this is supporting the null, I know what's at the middle here. I know that this is 16. They're saying the average is 16. Also, because it's left-tailed, we're saying it's less than 16. Over here is some spot that is far enough to the left that means our evidence, if we land over here, is enough to reject that the answer is 16. Okay, and this is called the rejection region. All right, now we need to figure out what this number is, but this number comes from our alpha. So since we have an alpha of 0.055%, I can find this number. Okay, now before I go any further, I do want to state that there are actually 3 ways of doing hypothesis testing. Technically, they're all exactly the same. We just may use different number lines. So what I'm doing here is I'm actually using the data. They claim it's 16 ounces. We're going to plop our results of 15.3 ounces on this number line somewhere, and I need to find this number of 5 percentile, what the 5 percentile, the bottom 5%, what number this is in terms of the ounces. I could also do this based off of all z-scores. I could find the z-score for 16, which would be easy. I could find the z-score for whatever the 5%, 5th percentile is, and I could take my 15.3 and convert it into a z-score and see where it falls. I could also, the third way would be to look at the probabilities of less than or equal to probability. So the probability right here would be to the left of that 50%. And we would find the spot where the 5th percentile probability or 5% of the population is to the left. And then we would see where our percentile falls. Those are called p-values, and those are actually really important to understand how to use, because later in the course we're going to be using R to spit a lot of things out at us. And what R is going to give us is just p-values, probabilities, how likely something is to occur. And that's it's good to understand that, but we'll just start with, we'll do it one way. We'll start with the data. And so what I need to do is I need to figure out what this value is at the 5th percentile. Okay. How am I going to do that? How do I do that? Well, what we need to do then is to back in these formulas, let me go back a page. I had these pieces right here. Well, therefore, as we tell it what our critical value is based off of our alpha, now this is a one-tailed test, so we're using the top one. We know the assumed average, and we found a standard deviation in a sample size, and this will tell us the value at the whatever critical value. So if we pick the critical value that matches the 5th percentile, the 5%, we will find the value of this number line right here at 5%. So that's what we're going to do. So using what we see, so I'll write the formula again so we don't have to try to hold it in our heads. So we're going to use the null hypothesized average added to the critical value, which means the z-score that matches an alpha of 5%, times our standard deviation divided by the samples, the square root of the sample size. And we actually have all these numbers. Now, we know that the claim is it's 16. Now, you may want to look up the critical value for 5% of a left-tailed test, but what that is, I'll put it in parentheses, is negative 1.645. We stated that in class. We wrote all these down. And then our standard deviation, oh, I already forgot it. Let me scroll up and find it. 1.2. Standard deviation's 1.2, and our sample size was 9, I believe. So there, a little bit sloppy. I'm sorry for the writing. I'm using a new pen and sketch pad. Have to get used to it. So if I put this in a calculator and do all these calculations, you should get 15.342. Maybe we can just get 2 decimal places, 15.34. So that's what this 5% spot is this number is on our number line is 15.342. So now, once I've found the rejection region spot, anything less than 15.342 means we can reject the null hypothesis. So let's go up and put our data on there. What did we get? We got 15.3. Where does 15.3 go? That goes over here somewhere. That's where our data is. It's in the rejection region. And so we can reject the null hypothesis. And so we want to write a statement that's carefully constructed, and I have that typed up for us. So that's what we start with, is we state whether we reject or whether we fail to reject. Because we're on the rejection region side of our critical value here, we can say we reject the claim that the average amount of marshmallows is 16 ounces. We conclude that it's less. Now, I can't conclude that it's 15.3 because that's just one small sample. But I do have enough evidence to say, hey, it's less. It's not 16. We're rejecting that it's 16, so we conclude it's less than. I need to be careful with whatever I conclude. I can't say it's 15.3, but it's less than 16. It could be 15.9. It could be 15.8, but we have pretty strong, well, okay, I'll save the word strong for the next lesson because we're going to look at the power of these tests in the next lesson. They're actually all pretty weak tests, but we'll talk about that later. But I'm in the rejection region, so I have statistical evidence to reject their claim that it's 16. And we found that it's to the left is less than. Okay? Now, to do this other ways, instead of having a 15.5 here, I could go with just percentages. So this is the bottom 5%. So all I need to do, and this value right here would be like 50th percent is lower than it. I would just need to see where my 15.3 falls percentage-wise. That wouldn't be too super difficult because I could just use R. So if I were to want to do this again, let me move some of this stuff out the way. So I would be doing the same experiment just with a different number line. And it's pretty simple. The rejection region here is just at 5%. I don't need this, but that would be the 50% mark. So I need to see where my data falls. And so all I would do is take what we found, and I could actually just put it in R using the pnorm function. Let's see, what is our data? 15.3. The average we're assuming is 16. And the standard deviation, I have to do that 1.2 divided by the square root of 9. And if you put that in R, I've done it somewhere. I got to find where I've written it down. I think it pops out somewhere around 0.4, so 4%, which, if you put that on our number line, is in the same exact spot that the data was using the percentiles. They're the probabilities. That's what these are. The probabilities are exactly the same in the same spots as the data that we had. So you could use probabilities to find whether you reject or not. And the third way would be to just similar to probabilities would be to use all z-scores. So you could take 16 and find the z-score of it, and it'd be 0. Take the 5th percentile. We know the z-scores of 5th percentiles. We already mentioned that. That's negative 1.645. And we would need to find the z-score of our data, which wouldn't be too difficult. Let me extend the page here. Oops, move. There we go. So to find the z-score of our data, we would just take our data, 15.3. This is the formula back on the other page for the z-scores right here. So we take our data, the 15.3, subtract what we assume is correct, 16, and divide by our standard deviation, which for us is 1.2 divided by the square root of 9. And if you were to use a calculator and calculate that value, you would get negative 1.75, which once again, where does that fall? It falls right here in the rejection region. So notice all three of these methods, we would have the distribution drawn over the top, but I was too lazy, are exactly the same. They're the same number line, just with different units, whether we're in ounces, the actual data, whether we're in p-values or probabilities, or whether we're in z-scores. Same exact thing. We would conclude the same thing. They would all be in identical spots. So those are the three ways to do a hypothesis test. Basically, they're all just different number lines. Now, I'll probably stick to data the rest of the way to go quickly, but I do want us to get cozy at some point with p-values, probabilities, because that's going to be important later in the course. Okay. But understand it's synonymous or exchangeable with these other ones. So let's do two more a little more quickly to kind of step through this. So we'll want to be careful and use these formulas to find the number value of our where our 5 percentile, where our alpha is. Okay, so let's look at this one. So we want to evaluate the average cholesterol level of middle-aged Chinese women to see if it's different from the average cholesterol level of middle-aged women. Okay. Now, there's some important things there. They go ahead and give us a big hint of what type of test we're doing because they're just seeing if something's different. Okay. So they have the average distribution of U.S. women. It's known to be approximately normal. That's good. That helps us out. We didn't have that information the last time, which might mean our test was not very good, but we'll ignore that for now. So the mean is 190 with a random sample of 100 Chinese female immigrants. They were administered a blood test, and we found the mean to be 178, and we got a standard deviation of 45. Okay, so let me try to highlight our important information. Sample of 100, average there is 178, and our standard deviation is 45. Now we're going to use an alpha of 0.05, a 5% level of significance, and we want to see that the cholesterol level, if it's different or not. Okay, so what are we claiming? What are they claiming? The null hypothesis here is that the average cholesterol level of the Chinese women is the same as American women, which is 190. Versus, now what are we trying to see or hoping to get at? We're trying to show as our alternative that it's not 190. They didn't say it was higher, they didn't say it was lower, they said it's not 190. That is different. So there's the key word. So because we're just looking for a difference, this means we have a two-tailed test. Okay, so what that means, why do I care to know that? That means when I draw the distribution of the null hypothesis, I know that we think the average is 190. We're saying, okay, we'll let you assume you're right. But what we're looking for is not something less than, not something greater than, but something that's either less than or greater than. Okay? And now we're looking at an alpha of 5% level. So that means that we're looking with 5% at the outside 5%. Now, this is split up over 2. So instead of being the bottom 5% of the data, this is actually the bottom 2.5% of the data and the top 2.5, which means it's like the 97.5th percentile. And these two areas are the rejection regions. So I have two areas. Because it's two-tailed, I'm looking for data in either end of these to be the rejection region. Okay? Now, what that means is we need to be careful with our formula, because if I were to go back to the formula page, there's that one slight difference. Let me go back and show you. One slight difference from one-tailed to two-tailed is it's still the same population mean, but what we're looking for is alpha over 2. So that's what I was pointing out as a 2.5 percentile, not the 5th percentile, for the critical value, the z-score there. Okay. So let's rock and roll this out. So if we were to take some time to do this, we're going to have two ends that we need to find. So we'll start with the 190 and we'll go plus. And what we found for that critical value, the z alpha over 2 is 1.96. That's our critical value times. And let's see, what was our standard deviation? I got to scroll up and find it. 45.3 divided by the square root of our sample size, which I think for this problem was 100. Okay, and then we'll do the same thing because z-scores are symmetric. On this side, the z-score was positive 1.96. On this side, it'll be negative 1.96. So minus 1.96 times 45.3 over the square root of 100. And we'll just use a calculator to find these two things. I've already done it for us. This one's 198.88, and this one is 181.12, assuming I typed them in my calculators correctly. So let's put these on the number line. And that is where they belong. So now I just look to see where my data falls. So let's see, what did we collect as data? 178. So where does 178 fall? Oh, that falls over here. That is in the rejection region. So what that means is we can reject the null hypothesis. So what we're finding is the Chinese women's cholesterol level is not an average of 190. Now, this time, because of the test I used, I did not claim it was less than or greater than. I claimed it was just not. So when I write my statement, I need to be careful about that. We reject the claim that the mean cholesterol levels are the same. All we can conclude is that they're different. We're not trying to conclude whether they're less, greater than. If you want to make a certain conclusion, then what you have to do is state that in your alternative hypothesis and do a one-tailed test. But we did a two-tailed test. Now, if you were to run these statistics, you probably would get that is less than, but that's not the point. Okay, being very careful with how we state things. All right, and then the last example, we'll go a little, even more quickly on that one. There's a new drug, they're testing it, and they believe that the drug is increasing patients' blood pressures. Okay, so let's see. So the average blood pressure in America is 122, probably higher now than when this problem was written. The clinician gathers blood pressures from 36 people. Okay, the patient's average blood pressure is 128 when they look at all the people in the trial, with a standard deviation of 20. Is there enough evidence to claim the new drug causes higher blood pressure? So let's see if we can write our statements. So let's see. Null hypothesis is that the average blood pressure is 122 versus our alternative hypothesis is that the blood pressure is higher than 122 when we're looking at our patients, because we're trying to see if the blood pressure is being risen or driven up. And so this is a right-tailed test. Right-tailed. So if I were to go in here and to draw my distribution, once again, it's kind of an ugly one, but that's okay. We're going to assume that the null hypothesis is true. So my number line here right in the middle is 122, and it's a right-tailed test. So that means that our rejection region's only in the right tail. And what we're doing is, once again, an alpha of 0.05. So I just need to find what number this is. And we'll use that same formula where I take the average, I add the critical value for the alpha, and I multiply by the standard deviation divided by the square root of the sample size. Okay, and I think I happen to know all these values. Let's see. So the claimed average by the null hypothesis is 122. Let's see, what's the critical value for, where are we at? A 5% alpha one-tailed test. We've done that already. We did a negative one, but it's a positive one. 1.645 times our standard deviation was 20, and our sample size was 36. And if you put that in a calculator, you will get 127.48. So this edge of the rejection region is 127.48. So if our data falls in there, we can reject. Okay? Now, what was our data? You go back and look. Oh, it was 128. Where does that fall? Oh my, it falls right here in the rejection region. Maybe I made bad examples because I made all three of them reject. I should have done one where we failed to reject. That's my fault, but I could change. We could pretend this was 126 if you wanted to and write it right there, and we'd say we cannot. We failed to reject, but it is what it is. So our statement, we reject the claim that the average blood pressure levels are 122 in our patients and conclude that the patient's blood pressure level is higher on average. So we can conclude that. So I hope that's an okay introduction into hypothesis testing. We spent a lot of time before this writing statements and talking about left-tailed, right-tailed, and talking about these critical z values and talking about what a significance level was. So today was just a jump into examples. So I hope that's helpful. Let me know if you have any questions, and good luck.